let's continue the lecture for section 3.4. So far from section 3.4, we covered the vector and parametric equation for a line. Yeah, so if you have a point, let's say P0, x0, y0, z0. My example is from R3, but it could be from any space. And you have a vector v that is parallel to the line. So let's say v1, v2, v3. Yes. So you have this is for a line in Rn. A point on the line and a vector that is parallel to the line will completely determine and specify the line. And now what would the equation be? The equation is going to be OP is OP0 plus TV. And if I write that in terms of the components, OP is X, Y, Z. That's could be thought of as a vector or as a point, because there is a correspondence between vectors and points if you put a vector in the standard position, and the vector OP is in the standard position. It goes from the origin to the point P. It's going to be x0, y0, z0 plus t times v1, v2, v3. So this is called a vector equation for a line. And if we just separate the x, the y, and the z and write them in the form of three equations like this, x0 plus tv1, y0 plus tv2, and z0 plus tv3, this one is called a set of parametric equations for that line. So today we're going to look at the vector and parametric equations for a plane. So in Rn, a unique plane is completely specified by a point P0 on that plane and two non-zero, non-collinear vectors v1 and v2 parallel to that plane. So what do I mean by that? So imagine that you are in the XYZ coordinate system, the regular three-dimensional space, and you have a plane, and you have a certain plane. So if you have a point on that plane, let's call that P0, yes, and you have two vectors, that are both parallel to the plane. So the vectors, we can call them v1 and v2. Then there is only one plane, there is only a unique plane that would be that these three items specify. So a point on the plane and two vectors that are parallel to the plane. Notice that the two vectors, both of them are needed, because if you have only one vector, you can think of infinitely many planes that pass through this point and are parallel to the vector v1. You can just rotate the plane around the v1, and all those planes satisfy this condition. You can think of infinitely many planes that pass through P0 and are parallel to v2 only. So just rotate the plane around this pivot. Think of v2 as a pivot and rotate the plane like this around that. You can see there are infinitely many planes that would pass through P0 and are parallel to v2. So you see, one vector does not work. You need two vectors, and these two vectors should be non-collinear. That means they should not be parallel with respect to each other, and they have to be non-zero vectors so that they determine a direction. So the moment you have these three items, a point and two vectors parallel to the plane, so two non-zero, non-collinear vectors parallel to the plane, then there's only one unique plane that passes through this point and is parallel to both v1 and v2. So these three items, these three pieces of information, they completely and fully specify a plane. So we should be able to write an equation for that plane using these three items. Yes. So notice that any point that is on this plane, any point that is on this plane is going to be a linear combination of V1 and V2. That means if I just multiply V1 by the right scalar and multiply V2 also by the right scalar, I'm going to get, for example, here, I'm going to get some T1 V1 and multiply this by a right scalar. So this new vector is going to be T2 V2. Then if I add up T1 and V2, T2, I'm going to get this point. So the vector that goes from the origin to P0, and then the vector that goes from the origin to this new point P, think of those two vectors. We can see that OP is going to be OP0 plus T1 V1 plus T2 V2. Yes, so the vector OP, which is an arbitrary point from the plane, is going to be the vector OP0 plus the sum of these two. And the sum of these two is going to be this vector here. It's going to lead us to P. Yes? So this vector that I have here is T1 V1 plus T2 V2. So this equation here is called the vector equation of a plane. For example, if I ask you to give me a vector equation for a plane that passes through the point P0, let's say 1, negative 1, 7, and is parallel to the vectors V1 and V2, let's say V1 is 3, 2, negative 1, and V2 is 4, 0, 3, yes, then that equation is simply going to be OP, which is our arbitrary point on the plane, x, y, z, is equal the OP0, which is going to be 1, negative 1, 7, plus T1 V1, 3, 2, minus 1, plus T2 V2, 4, 0, 3. So this here is a vector equation for the plane that passes through the point P0 and is parallel to both vectors V1 and V2. If I separate the x, the y, and the z, I'm going to get something called the vector equation, or the set of vector the set of parametric equations for the plane. So what do I mean by that? If you look at this, you can see x is 1 plus 3t1, and y is minus 1. So x is 1 plus 3t1 plus 4t2. Y is minus 1 plus 2t1 plus 0t2. I don't need to write that. And z is 7 minus t1 plus 3t2. So everybody sees that? So here, for example, for z, you can see z is 7 minus 1 times t1 plus 3 times t2. So in both cases, t1 and t2 are parameters. That means both t1 and t2 are members of the real number line. The real numbers, they're scalars. So this one here is called a vector equation for the plane. And this one here is called a set of parametric equations for the plane. The way you memorize that is that, you can see there are parameters in both of them, but this one is written in the form of a vector equation. So this one is a vector Yes. And so OP is a vector, OP0 is a vector, T1 is a vector, T2, V1 and V2 are both vectors. So for that reason, this is called a vector equation for the plane. And these are called parametric equations for the plane. T1 and T2 are the parameters. So notice that if I have a plane in the three-dimensional space, I can represent it using this method. That is vector equation or parametric equations. Or I can use the point normal method, which we learned in the previous section. However, if I have a plane from R4 or R5, then I cannot use point normal equations, because point normal equations, they only work for lines in R2 and planes in R3. If I have a plane in R4, then I can only represent it as a vector equation or a set of parametric equations. So we have this theorem here. Let W be a plane in Rn that contains the point P0 and is parallel to the non-zero, non-collinear vectors V1 and V2. Then this equation, OP, is equal OP0 plus T1 V1 plus T2 V2 represents W, the plane. Here, the vector OP, which is the arbitrary point from the plane, is considered to be equivalent to the point P. Again, because there is a correspondence between a vector in the standard position, like OP, and the point P. And the correspondence is that the components of the vector are going to be exact same as the coordinates of the point. So you can think of a vector like OP, you can think of it as a point. So particularly in R3, if W passes through the point P0, which is x0, y0, z0, and is parallel to the vectors V1, the vectors V and U, then the vector equation is going to be x, y, z, which is the arbitrary point, is equal P0, the given point, plus I can use T1, T2, I can use S and T, doesn't matter. Well, usually we use S, R, S, T for parameters. So here, since there are only two of them, I can use S and T. So SU plus T V. And notice that S and T are parameters, that is, they are arbitrary real numbers. If you take S to be 0 and if you take T to be 0, then you get the point P0. If you take, for example, S to be 1 and T to be 1, you will get another point from the plane. If you take S to be 3 and T to be minus 2, you will get another point from the plane. And you can, like this, you can get infinitely many points from the plane. And as S and T, as they go from negative infinity to positive infinity, this equation traces the whole plane. Now, if you separate the x, the y, and the z, you get x is x0 plus s u1 plus tv1, y0 plus su2 tv2, and z is going to be z0 is su3 plus tv3. And these are called the parametric equations. So this can be used to represent the same plane. This set of equations is called parametric equations. Now let's look at another example. Find a vector and parametric equations, A, for the plane through this point. So the point P0 is given, and parallel to the vectors V1 and V2. So it's going to be x, y, z is equal the given point, 1, 4, minus 5, plus I can use S and T. So S times V1, 203, plus t times v2, which is 1, 1, minus 5. Now, this would be the vector equation. If I want to write the parametric equations x, y, z, x is going to be 1 plus 2s plus t, y is 4 plus t, and z is minus 5 plus 3s minus 5t, where s belongs to real numbers and t also belongs to real numbers. So I hope you can see that this is very similar to the general parametric solution for linear systems. And I will show you also an example where when you find the solution to a linear system, as a result, you can get a plane as the solution set. I think I have an example here from the 4-dimensional space, and you will see that the result is going to be a plane in the 4-dimensional space. But before that, let's just continue with B. Any questions in part A? Is that clear, how I answered part A? We're just using the formula, yes? P0 goes here, then S V1 plus T V2, and then you can separate X, Y, and Z. That would be the parametric equations. Part B, find the vector and parametric equations for the plane passing through the origin and parallel to these two vectors from R4. So the point P0 is now the origin, 0, 0, 0, 0. And the two vectors V1 and V2 are also given. So I can write that x1, x2, x3, x4, because it's the 4-dimensional space, is P0, which is going to be the origin, plus S times the first vector, 1, 1, 2, minus 1, plus T times the second vector, 5, minus 3, 2, 1. This would be the vector equation. And if I separate the x1, x2, x3, x4, I can get a set of parametric equations. So it's going to be S plus 5t, S minus 3t, 2, S plus 2t, and finally going to be minus S plus t, where S and t are real numbers. So this one would be the set of parametric equations for this plane. Again, I want you to see the resemblance between this and what we were used to when we were solving the linear systems and we tried to find the general parametric solution. So for example, if you had two free variables, you would need two parameters, S and T, and your solution would look like this. Part C, it says, find a point normal equation for the plane in part A. So since the plane in part A is a plane from R3, I should also be able to find a point normal equation for this plane. Let's see what we have and what we need in order to write that point normal equation for the plane. So point normal equation for a plane in R3. So as the name suggests, we need a point and we need a normal. Do we have a point? We have a point. The point in part A is given, P0, to be 1, 4, minus 5. And we also need a normal. And what is a normal? A normal is a vector that is orthogonal to the plane. So we need a vector that is orthogonal to the plane. What we are given are two vectors that are parallel to the plane. So we are given two vectors like this, v1 and v2, that are parallel to the plane. But what we need is a vector that is orthogonal to the plane. So I want you to notice that if I find a vector that is orthogonal to both v1 and v2, then that can serve as the normal vector. Everybody sees the logic here? If you have two vectors v1 and v2 and both of them are parallel to the plane, if I am able to find a vector that is orthogonal to both v1 and v2, then that vector would be orthogonal to the plane. So v1 in this case is 2, 0, 3, and v2 is 1, 1, minus 5. So it's very easy to find a vector that is orthogonal to a two-dimensional vector just by inspection. When you have three dimensions, so you're in the three-dimensional space, then it's a little more difficult. But even in this case, it's possible because we have this one that is 0. So it doesn't matter what I pick for this one, for the normal vector. In the section 3.5, we're going to learn a method to get a vector that is orthogonal to two given vectors. And that's called cross product. And we will do that in 3.5. But for now, what we can do is I can take n to be, let's see, I can take n to be -3, 2, because if I pick -3 and 2, then it's going to be automatically orthogonal to v1, because here I have 0 and it doesn't matter what I put for the second component. When I do -3 times 2, I get -6. When I do 2 times 3, I get 6. And then it doesn't matter what we have here. N will be orthogonal to v1. Now, in order to make it orthogonal also to v2, we have to pick this middle component so that it becomes orthogonal. Now, let's see. If I multiply -3 and 1, we get -3. Multiply 2 and -5, we get -10. So -10 and -3, that's -13. So if I put 13 here, that will do the work. Because now if you multiply n and v1, you get 0. If you multiply n and v2, you also get 0. Does that make sense? Is this clear for everybody?
Yeah.
Okay, great. Now, I have everything that I need. I need a point, and I need a normal, and I have them. So I just plug in the values into the formula. A times x minus x0 plus b times y minus y0 plus c times z minus z0 is equal 0. So this one is going to be -3 times x minus 1 plus 13 times y minus 4 plus 2 times z plus 5 is equal 0. And then I can just expand this and write that in the form ax plus by plus cz is equal d. And I'm sure we can do that part. So I'm going to just move on to the next example. Okay, so example 5, it says find an equation for the plane of intersection between the following hyperplanes. So what is a hyperplane? A hyperplane is a geometric object of a dimension that is one less than the dimension of the ambient space. So here, this is an object from the 4-dimensional space, and itself is a 3-dimensional object. So that makes it a hyperplane. Same for the other one. But intersection between these two is going to be a two-dimensional object, as you will see, in a four-dimensional space. And a two-dimensional straight object in a four-dimensional space is going to be a plane. Generally, a plane is a two-dimensional object. Now, this sounds complicated, but the only thing you have to do is to solve this. That's all there is to this problem. Find an equation for the plane of intersection between the following hyperplanes. Because basically, when you're solving a linear system, that's what you do. You find the points of intersection. And those points of intersection, if you're dealing with a linear system, are going to be either a point or a line or a plane. So I just need to write the augmented matrix 1, 1, 3, 1, 12, 3, 2, 7, 4, 29. And then I can use the Gauss-Jordan elimination. R2 minus 3, R1, 1, 1, 3, 1, 12. Negative 3 times this to this 0, negative 3 times this to this negative 1, negative 3 times this negative 9 added to this negative 2, negative 3 times this negative 3 added to this 1, negative 3 times this negative 36, and negative 36 added to this is negative 7. So next I can do row 1 plus row 2. I get to get a 0 here. Add up these two, you get 1. Add up these two, you get 0. Add up these two, you get 1. These two gives us 2. And if you add up these two, you're going to get positive 5. And this row, I'm going to multiply that one by a negative 1 to get a 1 here. So we get 0, 1, 2, negative 1, 7. So basically Gauss-Jordan elimination. And then I'm going to write down the corresponding system. Since I have two leading variables, I'm going to have two free variables. There are 4 variables. 2 of them are leading and 2 of them are going to be free variables. And the equation becomes x1. I can use w, x, y, z. I can use x1, x2, x3, x4. I'm going to use x1, x2, x3, x4. Is minus x3 plus minus 2x4 plus 5. x2 is going to be minus 2x3 plus x4 plus 7. And then I can assign s to x3 and t to x4. Then this would make x1 to be minus s minus 2t plus 5. And it will make x2 to be minus 2s plus t plus 7. So the general parametric solution, which is going to have the form x1, x2, x3, x4 for this problem becomes minus s minus 2t plus 5 for x1, minus 2s plus t plus 7 for x2 becomes s for x3 and t for x4. So far, this is something that you should be familiar. This is the thing that we learned in the first week of the course, how to find the general parametric solution for a linear system. Now I'm going to show you that what we actually found is a plane. So if I just write it in the parametric equation, the parametric form, and by that I mean this form here, I will see it is a plane. So now I can write this that as x1, x2, x3, x4 is equal 5, 7, 0, 0 plus s times, I look at the coefficients of s, those are -1, -2, 1, 0 plus t times. Now I can look at the coefficients of t. I see -2 here. You see? Just need to look at the coefficients of t, -2. Then for the next component, it's 1. Then there is no t in the third component. There is no t here, yes? So it's going to be 0. And finally, there is 1t, so 1. So everybody sees that these two are equivalent. I can write the general parametric solution like this, or I can write it like this, and these are equivalent because x1 is going to be 5 minus s minus 2t, and then x2 is going to be 7 minus 2s plus t, and x3 is going to be 0 plus s plus 0, that's just s, and x4 is going to be 0 plus 0 plus 1 times t, that's t. But now that you have learned about the parametric equations and vector equation for a plane, you can see that this is basically the plane that passes the point 5, 7, 0, 0. That's the P0 here, and is parallel to the two vectors v1 and v2. -1, -2, 1, 0, and v2, -2, 1, 0, 1. So this gives you an insight to the geometry of the general parametric solution. The general parametric solution for a linear system like this is basically a plane in R4, because we had two free variables. If we had only one free variable, it would be a line. Now that we have two free variables, we have two parameters, s and t, that's a plane. So again, this problem, it may sound complicated, but the only thing you have to do is to solve the system. Any questions? Example 6. Given the points P0, 3, 1, -1, and the line, so you have a line from R3 and you have a point from R3. Part A, find a point normal equation of the plane passing through P0 and is orthogonal to the line. So let's see, what is this asking us? We have a line in R3. So this is R3, three-dimensional space. And you have a point also, P0. And this point P0 is outside the line. How do I know it's outside the line? I can just try to figure out, plug in 3 for x, 1 for y, and -1 for z, and try to find t. That is, solve the system. And if I don't find the t that is consistent to this, I will know that this is outside the line. So for example, if I plug in, let's say, 1 for y, because y is supposed to be 1. If I plug in 1 over there, then I can see that t has to be 2. But if I plug in 2 into z, I get 6. I don't get -1. Yes. So this point does not belong to the line. What is it asking us to do? It says, find a point normal equation of a plane passing through P0 and is orthogonal to the line. So you're looking for a plane like this. A plane that is orthogonal to the line and passes through P0. But in order to be able to write a point normal equation, we need a point and we need a normal. Yes, you have the point. You have the point. P0 is given. 3, 1, -1. But we don't have a normal, or at least we are not given a normal directly. What we can use is we can use the line, because the line, just by looking at this line, I can tell that this is a line that passes through, if I have x, y, z, and x is 3 plus 2t, and y is -1 plus t, and z is 3t. That means x, y, z is equal 3 minus 3, 0, plus t times 2, 1, 3. Yes, I just looked at the coefficients of t, 2, 1, 3. So you agree that these two are equivalent, yes? This is a set of parametric equations for a line, and this is a vector equation for the same line. So now I can see that this is a line that passes through this point, which is not useful for me for this problem, but is parallel to this vector. So I can get a vector that is parallel. I can get a vector that is parallel to the line. And that vector, I'm going to call that v 2, 1, 3. Now, do you agree that this vector, which is parallel to the line, I can use it as a normal vector for the plane? Because if it's parallel to the line, and the line is orthogonal to the plane, then the vector parallel to the line is going to be orthogonal to the plane. I can use that as a normal vector. So just plug in values into the formula. A times x minus x0 plus b times y minus y0 plus c times z minus z0 is equal to 0. Using the point for x0, y0, z0, and v as the normal vector. So we get 2 times x minus 3 plus 1 times y minus 1 plus 3 times z minus 1 plus 1 is equal to 0. So that would be a point normal equation for the plane that passes through the point P0 and is orthogonal to the line. Any questions? Okay. Now, it says find a point of intersection. Find the point of intersection between the line and the plane. So we had a line and we found an equation for the plane that is passing through this point P0 and it's orthogonal to the line. Now there should be a point of intersection between these two. Yes, I can call that Q. Yeah, Q is the point where the line and the plane meet. Yes, and notice that if we find Q, we actually have found the closest point on the line to the given point. So actually, if the question was find the closest point on the line to the given point P0, we would use this method. We would first find a point normal equation for the plane that passes through P0 and is orthogonal to the line, and then we would find the point of intersection between the plane and the line. Okay, now let me explain to you how you can find the point of intersection between a plane and a line. Okay, let me just use this and write it in, expand it. We get 2x minus 6 plus y minus 1 plus 3z plus 3 is equal 0. That means 2x plus y plus 3z is equal, let's see, minus 6 minus 1, that's minus 7. Minus 7 plus 4, that's minus 4. Let's move it to the other side, becomes 4. Okay. And what about the line? The line is given here. In order to find the point of intersection between the line and the plane, I'm actually looking for a certain point that satisfies the equation of both objects. Yes. So what I can do is I can plug in this value for x. I can plug in the next one for y and the third one for z into the equation of the line, and then find t. That would be the value of the parameter which will generate the point of intersection between the two objects, because it will satisfy both. Yes. So let's just plug in 3 plus 2t for x plus negative 1 plus t for y plus 3 times for z, I need to plug in 3t is equal 4. So that's the only thing I need to do. Plug in x, y, z in terms of t into the equation of the plane. We get 6 plus 4t minus 1 plus t plus 9t is equal 4. So that means 14t is equal that's positive 5, goes to the other side, negative 5, negative 1. So t is negative 1 over 14. Now, if I plug in this t into these three equations here for the line, I'll get the point that will satisfy both equations, the line and the plane. So let's do that. X is 3 plus 2t, so I replace that with minus 1 over 14. Y is negative 1 plus t, so negative 1 over 14. And z is 3 times t, so 3 times negative 1 over 14, giving me negative 3 over 14. Here it gives me, this is like having a negative 14 over 14, that's negative 15 over 14. And this one, I'm going to use a calculator for this one. 3 plus, actually 3 minus 2 over 14. That gives me 20 over 7, or 40 over 14. So the point of intersection, which is Q in this diagram, which is also the closest point that you can find on the line to P0, is going to be 40 over 14, negative 15 over 14, and negative 3 over 14. Is that clear? So here I have added a note. Note that the point that we just found in part B, the point Q, is the closest point on the line to P0. Yes, there are many points on this line, but the closest one to P0 would be Q, which is the point of intersection between the line and the plane we found in part A. Any questions? Next example, find a vector and parametric equations for this plane. So if I give you the plane x minus 2y plus z equals 3, which is equals -3, which is a point normal equation for a plane in R3, you should be able to find a vector equation for that, or parametric equations for that. It's super easy. The only thing you have to do is to assign parameters to z and y. So you can write this as x is equal to y minus z minus 3. And then you can say y is s and z is t. So this becomes 2s minus t minus 3. So I can write the same plane as, it's as if I'm solving it as a system, but as a system with only one equation. 3 unknowns, only one equation. And what do I get? I get 2s minus t minus 3 s t, which I can also write as, if I need the vector equation, I can write that as x, y, z is equal -3, 0, 0 plus s times 2, 1, 0 plus t times -1, 0, 1. So basically you can see that this is actually a plane that passes through this point and is parallel to these two vectors. And I was able to write a vector equation for the same plane. I was able to also write a parametric equation, a set of parametric equations for the same plane. So it's very similar to this problem that we did. Here, you just solve the system. And you do the same thing for this one. You just solve it as if it's a system of equations with only one equation. Are we good? Next problem. Find a vector and parametric equations for the line that passes through these 2 points. So if you have 2 points, point A and point B, and you want to find the equation of the line that passes through these 2 points, A and B, you can use vector equation. You only need one point and a vector that is parallel to the line, but the vector that is parallel to the line is AB, right? So I can take V to be the vector AB. If both A and B are on the line, then AB will be parallel to the line. And in this case, AB is going to be what? Terminal minus initial. So 4 minus 3, 1. -1 minus -1, 0. And 5 minus 5, 0. Right? 4 minus 3, 0. -1 minus -1. And 5 minus 5. Good. And for the point, I can use point A. Or point B, doesn't matter. I just need a point and a vector. So it's going to be x, y, z is equal, just remind you that it's going to be like this, OP0 plus TV. Yes? So it's going to be x, y, z is OP0. I'm going to use A for that. 3 minus 1, 5, that's the point, plus TV, 1, 0, 0. And since it is asking us for the parametric equations, I'm going to separate the x, the y, and the z. X is 3 plus t, y is -1, and z is just 5. X is 3 plus t, y is -1, and z is 5, where t is all real numbers. There are some problems where it is asking you only for the line segment between A and B. So imagine you have these 2 points A and B, and you don't want the equation of the whole line that passes through A and B, but you only need the equation for the line segment. So that segment of the line between A and B. It would be the same thing. You would do the same thing, except for you let t to only move between 0 and 1. Because if you take t to be between 0 and 1, then it will become the equation of only the line segment. When you plug in 0 for t, you're going to get the point A. Yes, just imagine if I plug in 0 into this, I get 3, negative 1, 5. That's A. And if you plug in 1 into t, you get 4, negative 1, 5. And 4, negative 5, 1, 5 would be point B. And then when you plug in the values between 0 and 1, you get the points between A and B. Actually, if you just plug in exactly 1.2, I guess you're going to get the midpoint between A and B. So for example, if t is 1 and 1 over 2, then you get this point, let's call that C. That would be the midpoint between 1 and B, A and B. Anyway, if you see in a problem, it is asking you for the line segment between the points A and B. That's the only difference. If you let t to be any real number, then you get the whole line, which stretches on both sides to infinity. But if you let t to only vary from 0 to 1 for the same set of equations, you're going to get a line segment, only the line segment between A and B. For 0, you get A. For 1, you get B. And then for any number between 0 and 1, you get the points that are between A and B on this line. Make sense? Example 9. Find a vector equation for the plane that contains these 2 points and the origin. So imagine if I ask you to give me an equation of a plane that passes through these 3 points. So we have 3 point A, B, C. These 3 points, of course, they form a triangle. But there's also a plane. There's also a unique plane that passes through these 3 points. If I just give you 3 points, those 3 points together, they completely and they fully specify a unique plane. So that should be enough information to write down the equation of that plane. So it's very easy to ask yourself, what do I need? I need a point, and I need 2 vectors parallel to the plane. Then I can just plug in values into this formula. Or I can use S and T, doesn't matter. But if I have 3 points, I can use, for example, point E as the given point. And then I can use AB, the vector AB, and the vector AC as V1 and V2. Does that make sense? So in this problem, one of the points is the origin. So imagine point A is the origin. So imagine, yeah, here you have one of the points is the origin. It says to contain the points A, B, and the origin. So the vector that goes from O to A is a situation like this. This is, let's say, point A, this is point B, and this is the origin. So for this problem, the vector OA is going to have the same components as point A. So I can use -1, 1, 2. That would be the same as the vector OA, and the vector OB, I can use that for the second vector. The vector OB is going to be 320. 320. So let's just use the origin as the given point, OP. I'm going to use XYZ. XYZ is going to be 0, 0, 0, which is the origin, plus T1, V1, negative 1, 1, 2, plus T2, which is 3, 2, 0. So notice that in this problem, I used the origin as the given point because the origin is a point on the plane. And I used the vector that goes from the origin to A as V1 and the vector that goes from the origin to B as V2. So what you have here is actually OA, and what you have here is OB. However, since it's a vector in the standard position, the components of the vector are going to be the same as the coordinates of the point. However, if you're given just 3 points, A, B, C, and none of them is the origin, you can easily get V1 and V2 just by calculating AB and AC. Yes, just use the formula terminal minus initial, you can get the vectors. Next problem. Show that this line lies in this plane. So you can have a plane and you can have a line, and the line can lie within the plane. But how do you prove that? It's very easy. You just need to plug in. You have x is 1 plus 3t. You have y is negative 1 plus 2t. You have z is negative 1 over 6. So you just plug in this for x, you plug in this for y, and you plug in this for z in the plane, and you see whether you get 4 on the other side. If you get 4 on the other side, it means that every point in the line satisfies the equation of the plane. That makes the line to be in the plane. That's one way of doing it. The other way of doing it would be find 2 points from the plane, from the line, and make sure that those 2 points also are in the plane. Logically, since both of them are flat, if 2 points from the line also belong to the plane, then the whole line is within the plane. But the first method is easier. Let's just plug in 2 times 1 plus 3t plus, it's minus 3 times minus 1 plus 2t plus 6 times negative 1 over 6. This is supposed to be 4, yes? I just plugged in the values from the line into the plane. That gives me 2 plus 6t plus 3 minus 6t plus minus 1 is, okay, this cancels this. I get 5 minus 1, 4. Check. If I got anything but 4, I would know that no, this is not the case. But now that I got 4, that means every point in the plane, in the line, also satisfies the equation of the plane. Example 11. Find the point of intersection between the line in the previous example, so this line, and the plane XZ. So let's say this is XYZ, and the plane XZ would be this floor here. And if you have a line, that line can intersect with the plane xz at some point. How do you find that? Notice that any point in the plane xz has a y coordinate that is equal to 0. You agree? Any point in this plane, any point in the plane xz has the form some x, it has some z, but the y coordinate is going to be 0. Actually, this is the equation for the xz plane. This would be the point normal equation for the xz plane. So the only thing I need to do, I need to make, in this equation here, I make y equals 0, and then I find t. The moment I have t, I also have x and z. So I have x is 1 plus 3t, y is minus 1 plus 2t, and z is minus 1 over 6. So if I plug in 0 for y, minus 1 plus 2t, that gives me t is 1 over 2. Okay, now that I have t, I can plug in t into x and z to get the point of intersection. So if I plug in 1 over 2 into here, I'll get 1 plus 3 over 2, that's 5 over 2. So x is 5 over 2. Y is, of course, 0. And z is a constant negative 1 over 6. So the point of intersection is going to be the point 5 over 2, 0, and negative 1 over 6. So that's how you find the point of intersection between a line and one of the three planes here, the xz or the xy or the zy. You just need to figure out which one of these three coordinates need to be set to 0. Then you find t, and then from the t you get the other two coordinates. Example 12. Find an equation of the plane through this point and parallel to this other plane. I have given you example like this before, so I just explain it and then quickly go to the next one. If you have two planes and if they're parallel, then normal vector from one plane can also be used as the normal vector for the other plane. Yes. So if you have, for example, the plane that passes through this point P0 and is parallel to the other plane, you can take the normal vector from the other plane and use that and the given point to find the equation of the parallel plane. So that is easy. Let's just move on to the next one. You understand this one? Find an equation of the plane through this point and parallel to this other plane. So you have a point and you get the normal from this one. The normal would be 6 minus 2, 1. So number 13, find an equation for the plane that contains this line and is perpendicular to this plane. So this is a little more difficult. You have a line. You have a plane that contains this line, and that plane is also perpendicular to this other plane, and you're looking for the equation of it. So it's like this. You have a plane, and let's say this plane contains a line like this. And this plane is also perpendicular to this other plane. So what you can do is you can take one of the points on the line. You can use the vector parallel to the line, and you can also use the vector that is orthogonal to the plane, to this plane. And then this would be enough information to write the equation of the unknown plane. Does that make sense? If I want to write the equation of this plane over here, what do I need? I need a point on that plane, and I need two vectors that are parallel to the plane. Since the line is contained in the plane, I can use a vector that's parallel to the line. That I can get from the equation. And for the other vector, I can use the normal vector for the plane, because these two planes are orthogonal. That means the normal vector to this plane would be parallel to this plane. So by looking at this line, I can see that this line passes through the point P0, 2, minus 1, 0. Yes, 2, minus 1, 0, and is parallel to the vector, I call that V1. Let's just look at coefficients. We get 1, minus 2, 6. 1, minus 2, 6. And then for V2, I can use the normal vector for this plane. Yes, the normal vector for this plane is 2, minus 1, minus 3. 2, minus 1, minus 3. And that's it. I just use the formula OP0 is equal P0. Sorry, OP is OP0 plus T1 V1 plus T2 V2. So it's going to be XYZ is equal 2 minus 1, 0 plus T1 V1 plus T2 V2. Okay, I just want to finish this. I'm not going to cover the optional part, but I just cover, I maybe need 3-4 minutes to cover example 14 and 15 so that we are done with this section. Find the closest point on this plane to this point. I just explain that and I let you try it. You have a plane and you have a point. And you want to find the closest point. Let's call that point P and this point Q. You're looking for the point Q that is closest to the point P on the plane. What you can do is this. You can find an equation of this dashed line, the line that is orthogonal to the plane and passes through P. And it's very easy to do because you have a normal vector for the plane. And the normal vector for the plane is going to be parallel to the line. So you find the equation of that line, and then you find the point of intersection between the two. So that's how you do this one. Is it clear? Okay. And then for number 15, find the closest point on this line to this point. I did an example like this earlier. So this is similar to example 6. Number 15 is similar to example 6. You have a line. And you have a point that's outside that line. And you're looking for a point, let's call this P and let's call this Q. You're looking for Q. You're given P, you're given the equation of the line, you're looking for Q. What you can do is you can find an equation of a plane that passes through P and is orthogonal to the line. How you do that? You can write a point normal equation because you have a point and you have a normal. A vector that is parallel to the line is going to be orthogonal to the plane. So use this as the normal vector. If you have the equation, the point normal equation of the plane that passes through P and is orthogonal to the line, then Q is going to be the point of intersection between these two objects. So that's the method. You do it in 2 steps. Step 1, you find the equation of this plane using the normal vector that you get from the line. And then you find the point of intersection between the plane and the line. That would be the closest point on the line to the plane. Okay, I'm going to let you work on number 14 and 15 on your own. And there are also some problems like this in the web work. You can ask me your questions next time. Do you have any questions for now?